All right, I'm not quite sure why it stopped, but hopefully we didn't miss too much. So just to quickly recap, we have AS, satisfying this inequality over here. It's not feasible for the dual, so we're going to make a switch. We now write things out like this. This is going to be a new feasible solution so long as these numbers here are what? What do we? They need to be positive. So if we choose lambda to be positive, that's no problem here. Well, what about these ones over here? Well, x1 and x2 are positive. If we start off at lambda equals 0, everything is fine. If we start turning up the lambdas, then for sufficiently small lambda positive, this will still be positive. Now it turns out here, t1 and t2 are both negative. So as we keep increasing lambda, it looks like that is always going to be positive. So then the question is, do we want to be increasing lambda or decreasing lambda? I think we want to increase lambda. So we've got to increase lambda. So we could keep increasing all the way up to infinity. Okay. Okay, so for this problem they're saying we actually can increase up to infinity. Good. It's looking like there's not going to be an optimal solution. And the reason why it's looking like there's not going to be an optimal solution is there is no optimal solution. So t1 is negative 1. t2 is negative 1. So we can send lambda to plus infinity. And as we send lambda to plus infinity, what's going to happen is this is always going to be a feasible solution. And the cost is going to be going down with lambda. So the cost is going to go off to minus infinity.
So what is the cost in this problem?
So the cost is going to be, the C transpose X.
But just what is C?
Oh, I don't remember what C was. So the cost here is x1 plus x2 minus 3x3. Okay. And so here we have this whole chain of solutions. Let's think about what could have happened. Imagine, for the sake of argument, that one of the t's was not negative 1 but was positive 1, so we still had a minus sign here. If we had that situation, then as we increase lambda, eventually when lambda equals x2, this would now become 0. And we would now have two coefficients again, and we would now have exchanged column A2 for column A3. And that would be our new feasible solution. Positive, positive, 0. We can't have two things becoming 0 at the same time. If we did, that would violate B, I think, being a linear combination of exactly two columns here. And so in the general case, we would increase lambda, and if we could only increase lambda up to a certain amount, then we've now switched A2 for A3. So we're switching out one column for another, and that lowers the price. And now we would have a new basic feasible solution. Well, now that we have a new basic feasible solution, lather, rinse, repeat. We feed it back in, we apply phase 2 again. And then we keep doing it. Could we end up stuck in this infinite loop doing phase 2 infinitely often? No. Either eventually at some point we're feasible for the dual problem, or every time we go through this, the cost is lower. The cost has gone down. There's only finitely many basic feasible solutions. And so if every time the cost goes down, we can never repeat a basic feasible solution, because if we repeated a basic feasible solution, it would have to be a lower cost. And if you give me the same solution and I just look at the solution again 10 minutes later, its cost can't go down. Now, if you think about this, it's not surprising in hindsight that the cost can go to minus infinity. This is not a strange matrix. This is a very, very specially chosen matrix. Can you find a choice of x1, x2, x3 such that when you apply this, you get the vector 0, 0? 1, 1, 1. So if you applied the vector 1, 1, 1, you get 0, 0. So if I take any feasible solution and I add 1, 1, 1, I get a feasible solution. So if instead of taking 2, 1, 0, I could take 2 plus maybe some big B. I'll do it in vector form. 1 plus big B and big B. And now what's the effect of b coming in here? We'll have b plus b minus 3b. That gives us a negative b. So I can essentially, whatever the cost of 210 is, okay, I put in 210, that gives me a cost of 3. I'll get, the cost of this is going to be 3 minus b. I send b to infinity, and I can drive the cost to infinity. So because there's an element in the null space of this, there's an element that's sent to 0, and because that has a negative cost, I can just keep taking higher and higher multiples of it. It's extremely important that the vector 1, 1, 1 has all positive entries, so I can add any multiple of it and not change what's going on. So this is essentially an example of how you would go through and use the simplex method. So again, in terms of actually doing things, computer programs will do all of this for you. This is the algebra of how you do the steps. This is the linear algebra. It's this game of trying to find a basic feasible solution at first. You can either do it by divine inspiration, you can do it by trying a few different choices of columns, you can try it by putting in the identity matrix and then looking for the trivial solution and then applying phase 2 to it. That will always work, but it's time intensive. If I give you a quadratic polynomial, can I find one where you can't find the roots? I want to find a quadratic polynomial that is beyond your ability to find the roots. Can I do it? Can I stump you? No. What would you use? You'd use the quadratic formula, right? Would you enjoy it if I chose a particularly bad polynomial? Hell no. But I can't stump you. It's a method that's guaranteed to work. Putting in the identity matrix and applying phase 2, that's guaranteed to work. But it's not guaranteed to be fast, because you've got to go through all of the phase 2 calculations. If you can find a basic feasible solution by divine inspiration, more power to you, and that will save time. The question then becomes, maybe one solution is a better place to start than another. Right? Maybe you want to do one rather than another. That's a harder question. But, all right, so I hope this helps explain a little bit of the simplex method.